The best way to learn Newton's second law is on a space train. Along the way, we'll look at some other interesting phenomena like dropping two tennis balls tied together, or dropping a slinky. We'll check out a Desmos. So let's go on the adventure. Now, you could teach using 3 blocks on a frictionless surface tied by massless rope, and that's fine, but it's more fun to take a space train. By space train, I just mean it's isolated, not necessarily that it's in space. So let's say you have 3 10-kilogram blocks tied together with a 90 Newton force pulling the front of the train. What's the acceleration going to be? What are the 2 tensions going to be? So to answer this, we're going to use, you guessed it, Newton's second law. F net equals ma, and I like to call it Newton's second law both ways, which also means the sum of the actual forces involved. Now, the first way I'll teach you to do this is applying Newton's second law to each of the 3 objects individually. Start by drawing a free body diagram. First for car 1, then for car 2, notice the tension 1 and 2 is the same magnitude, both on block 1 and on block 2. Then on block 3. Now let's use Newton's second law. First on block 1, then on block 2, then on block 3. Now at this point it's worth noting that there are 3 things we don't know. Tension between blocks 1 and 2, tension between blocks 2 and 3, and the acceleration. Notice there's only one acceleration because the whole train moves together. If it didn't, it'd be chaos. One of the things you learn doing physics is that you always want to have at least as many equations as you have unknowns. So now we have 3 simultaneous equations. Now it's just math, but notice tension 1 and 2, tension 1 and 2. So we're going to plug this in for tension 1 and 2, like that, and then let's solve that for tension 2 and 3, which you notice this tension 2 and 3 is the same as this tension 2 and 3. So we're going to take this and plug this in for tension 2 and 3, which you then just rearrange for FA. And then we plug in the values, which gives us 3 meters per second squared. I'll circle that in some celebratory purple, which you then just plug back into here and here to get the 2 tensions, which will also box in some celebratory purple. So for this space train, we figured out that the tension of 2-3 is 2/3 of the tension, or the applied force, and the tension 1-2 is 1/3. That's interesting. What if I told you there's a slightly faster way to get the acceleration of the train? It's called the system approach. And what you do is you think of forces as being inside or outside of your system. So if we put all of the mass in the system, it's like you have one thing that has a mass of 30 kilograms. So you can just use Newton's second law on one block like we did in the very beginning, which gives us the same answer, 3 meters per second squared. Now that is definitely cause for some celebratory purple. Now there's even more cause for celebration. Now that we know the acceleration of the system, if we were to look at just the rear 2 cars, it's like one thing that has a mass of 20, but we already know the acceleration is 3 meters per second squared. So tension 2-3 is the net force, is going to equal m times a, so this is our new system, which gives us the same thing. That's interesting. But if you think about it, it makes sense. F net equals ma. Since these all have the same acceleration, if you want to think of it as external force on part of the train, is proportional to the mass. So the fraction of the mass in the train behind where you're looking is the same as the fraction of the applied force to the whole train that tension is going to be. If all that sounds confusing, I made a Desmos simulation to show us what this looks like. So what's going on here? This is a little Desmos model I made. And these are the trains. So this is 10 kilograms, this is 10, this is 10. You can adjust it. We're applying a force of 90, which, by the way, we can change by just sort of dragging it up or down. And you get a tension of 60 newtons and 30 newtons for an applied force of 90, just like we expected. Now visually, look at these arrows and think about what's going on. We have Newton's third law pairs here. And notice this arrow is the same size as this arrow is the same size as this is the same as this is the same as this, and this is the applied force. So the relative length is proportional to the force. The black arrow is the force applied to the whole train. So let's see what happens if we change the sizes of the masses. I'm going to make the math a little easier. I'm going to make that 100 newtons for the applied force. We still get 2/3 of 100 and 1/3 of 100. But what if I made the middle train a mass of, say, 20? How does that change things? Well, you can see this tension is 75 newtons because 3/4 of the mass of the train is behind this point. This is only 25 newtons because 1/4 of the total mass of the train is behind. What if I make mass 1, say, 70? That's pretty massive. Now you can see this tension is 70% of the weight, and this is 20%. I should say 20% more. It's 90% because 90% of the mass of the train is behind this point. Well, that's cool, but what if we tried to do this in real life? I did try to do it in real life, and here's what it looked like. So I took a slow motion video of me pulling a cart with a spring scale, and then a second cart behind here connected by a spring scale. These are both 3.2 kilograms. Now it might not work perfectly, partially because these scales have mass, partially because it's a little bouncy, but watch what happens. May have been hard to miss, or I should say may have been hard to see. So I took a screenshot, and at this moment in time, I got 6.6 newtons over here for the first scale. That's like the applied force. And for the scale attached to the second cart, I was getting 3.2 newtons, which isn't quite a half. It's actually a little bit less, but that actually makes sense. Because here, when you're pulling, you've got the mass of this cart, and the mass of the spring scale does come into play a little bit. Now here I think it's dwarfed by the friction in the wheels and my ability to pull a constant rate and just the nature of using a spring scale while you're in motion. But that worked pretty well. I was pretty happy with that. Now there's some other pretty neat things we can look at. I want you to imagine that I had a 5-car train, and each car had a mass of 20 kilograms and I pulled with 100 newtons. What would these tensions be between each of the train cars? If you've been following along, you might quickly realize that, well, over here is 4/5 of the mass of the train, so the tension between these two should be 4/5 of 100, or 80. Between these two, we now have 3/5 of the train behind us, so 3/5 of 100 is 60. Over here's 40, 20. That's cool. But what if the trains were not the same mass? In fact, what if the green car had no mass at all? So if I make that go all the way to 0, what happens? Well, the mass of the train is now 80. So at this point here, you now have 50% of the mass of the train behind you. So that's 50 newtons. At this point here, you now have 3/4 of the train behind you, so that's 75 newtons. Other things to notice. When you're looking at the actual forces acting on each individual train car, for all of the cars that have mass, the two arrows are different sizes. They have to be, because the net force has to be to the right. The net force has to be bigger. So this purple arrow is bigger than this green arrow is bigger than this red arrow, this orange arrow. Well, that's the only orange arrow. In fact, because these are the same mass, this is the net force on this car, and the difference between these two will actually be the same size as this, just because all cars are the same mass. But what's going on with M3? Why are they the same size? One way to think of this is that for any car, the tension in the front minus the tension in the rear of that particular car is the net force on that car. And that has to equal ma, because that's Newton's second law. But if the mass is 0, that means that these two forces have to have the same magnitude. They're just opposite directions. So these two forces have to be the same. So let's see what happens if we start making some of the other masses 0. If I make this mass 2 go to 0, you'll see this is a third of the mass of the system, so the tension is a third of the applied force. You'll also notice that the tension in this car, mass 2 and mass 3, is identical. Because there's no mass, these forces have to be the same. If I do here, it's the same. And if I do here, also the same. In fact, you could think of this no longer as a train car and instead as rope. So when we do most problems in physics classes, we assume the rope is massless, but it doesn't have to be. By the way, if you want to try this Desmos simulation yourself, you can go to this link, or I'll also link it in the description of the video. So here's another neat application. I want you to imagine that you have 2 tennis balls. They're connected by a rope. So if you hold this first tennis ball with your hand, and then you let it go, what's going to happen? Which tennis ball will hit the ground first? Do they fall together, or does one hit the ground before the other? Is there a good reason? Hint, yeah, there's a good reason for the answer, but what do you think the answer is? So here's a video, at least over a short distance, of the tennis balls falling. So I'll just play this like so. And you can see the top one is starting to take a look at the bottom one. It's catching it up. Doesn't catch it all the way in a meter, but eventually it will. So here's a couple screenshots in case you didn't catch that. It is getting closer. So what's going on? Newton's second law. Let's start with the free body diagram. On the top tennis ball, what are the forces acting on it? Well, there's the weight force, mg, but there's also a tension pulling down. And that tension is going to have a magnitude, at least initially, that's equal to mg because of the mass of the lower tennis ball. You're providing an upward force that's equal to the sum of those two, so that's your applied force. Notice the net force is 0. Now at this tennis ball, you've got 1 mg going down, you've got 1 tension which is equal to mg. That also is an F net that's equal to 0. So what happens when you take your hand away? Well, it's almost the same, but now the applied force goes away. The net force on the top ball is now equal to 2 mg because of the tension. It doesn't go away instantaneously. There's a little bit of a delay because of the inertia of the ball. And the bottom ball has a net force now that is still 0. So for a brief moment, the bottom ball is not moving at all, and the top ball is moving downward with an acceleration that starts at around 2g. Now, as this ball starts to move, that force drops as they get closer together until eventually both balls are falling at g. So as this tension decreases, the bottom ball the acceleration starts getting closer to g from 0, and the top one decreases from around 2g to g. But because this top ball had the higher acceleration, it had an initial velocity, and it eventually overtakes the bottom ball. But it gets even weirder than that. What do you think happens if we hold a slinky like this and we let it go? So what do you think is going to happen? Let's see. Alright, that was a little quick, so let's go back here. I want you to pay particular attention to the bottom of the slinky. So it's jiggling a little because it was bouncing when I took pressed the button. So I let go at the top with my hand, and the bottom is not initially moving. To make it easier, here's a sequence of 5 shots from the video. Notice the bottom of the slinky is not moving. You let go, and then this starts to go, and then this starts to go. This is actually a lot like the tennis ball we just let go. Notice the rings of the slinky are farther apart here, closer together here. The reason is, the higher up on the slinky you are, the more of the slinky is hanging below you, the more that weight force is. So when I'm holding with my hand, I'm pulling up with the entire weight of the slinky. You can think of it almost like we had just a series of tennis balls connected by massless springs. The top tennis ball, the spring is going to stretch farther than the tennis ball below it, which is going to stretch farther than the tennis ball below it. So in this little simple model, it's like you would have a tension of 3 mgs because of the 3 balls below it, plus the 1 mg of the weight, so 4 mgs, and then I let it go. This tennis ball would have an acceleration of something like 4 Gs. And then it would decrease as the spring got lower. Well, these balls down here don't actually know anything has happened yet until this ball actually moves. And then this ball actually moves. It takes time for that to happen because of the mass involved. It's almost like there's a signal propagating and there's a delay because of the inertia of the spring itself, of the slinky itself. Just a neat little tidbit. If you know anything about center of mass, you might wisely or astutely say that the slinky still has to fall at G because the only force acting on it that's an outside force is the weight force. And that's true. The center of the mass of the slinky will fall down at G, even when the bottom of the slinky is not moving. So because the top portions of the slinky are falling at greater than G, and the bottom of the slinky is accelerating at 0, the center of the mass is still falling at G, which is, it's kind of neat. So this has been a little bit of an adventure, a little bit of a rodeo. I hope that somebody out there found this useful and maybe even interesting. I think definitely calls for purple.